Alright, part 2, chapter 2. Percent of modulation. Before we explain 100% of the modulation in an FM system, let's review the condition of 100% modulation of the AM wave. Recall that 100% of the modulation AM exists for the amplitude of the modulation envelope varies between 0 volts and twice the normal unmodulated value. At 100% of the modulation, there is no power increase of 50%. They cover the modulation wave is not constant in voice signals. The degree of the modulation constantly varies. In this case, the vacuum tube of the AM system cannot be operated with the maximum efficiency because of the varying power requirements and frequency modulation. 100% of the modulation of the being different from the AM, that of AM. The modulation signal varies with the frequency of the carrier. Therefore, the tube does not have the varying power required that it can be operated with the maximum efficiency for the FM signal with a constant power output of the FM modulation of 100% simply means for the carrier to deviate with the frequency by the full permissible amount. For example, 88.5 megahertz for the station operates at 100% modulation. When the modulating signal develops the frequency bandwidth of 75 kilohertz and 75 or above, 75 kilohertz or above, the 75 kilohertz below, but the carrier the maximum allowable limit. The maximum deviation frequency of the standard arbitrarily will be varying according with the application given with the FM transmitter. In the case given above with the 50% modulation would mean that the carrier would deviate at 37.5 kilohertz. Above and below the resting frequency of 50% with the 150 kilohertz bandwidth divided into other assignments of the FM server. This may be the limited amount of the deviation of 50 kilohertz or even 10 kilohertz. And if there is no fixed value for the comparison in terms of the percent of the modulation, has little meaning for FM. The term modulation index is more useful for the FM modulation discussion. Modulation index of the frequency deviation divided by frequency of the modulating signal. Modulation index with the ratio frequency, deviation frequency modulation signal with the usually because of the describe the ratio, amplitude of the tone of the audio signal. The factors determine the number of the spacing the sign. Frequency of the transmitted signal. The modulation index formula is shown below. The modulation equality is equal to the frequency over frequency of deviation over the modulation frequency. In views A and B for the 2.9 show the frequency spectrum varies from the signal. In, for example, the view A with the modulating frequency is common with the deviation frequency is changed to show that the effect of the modulation is half, 1, 5, and 10. In views B with the deviation frequency is held, but the constant modulating frequency varied and given them the same modulation index. Alright, so the modulation index is equal to the frequency deviation over the modulating frequency. Show that the amplitude 1 kilohertz half frequency deviation 1 point frequency deviation 5 point frequency deviation 10 point frequency deviation. FM is equal to the modulation frequency FM over the and FM frequency deviation over the FM modulating index. Alright, you can determine the several factors of the signal state with the frequency spectrum. For example, the table 2.1 that developed the information for the ticket 2.9. Note at the top of the spectrum both view A and B with the modulation index of 0.5. Also, now you look at the next lower spectrum, then the modulation index 1.0, next to 5.0, and finally the bottom spectrum has the modulating index. Frequency deviation with the triangle F, and then FM is modulation, frequency, modulation index, frequency, modulation, frequency deviation over frequency, modulation frequency. The index of 10. The information for the developed in the table 2.1 with the listing for the modulation index with the left of the column, and with the significant sideband with the right with the significant sideband. Those are the significantly large amplitudes are shown by both the U for the figure 2.9 vertical lines each side of the carrier frequencies. Actually, with the infinite number of the sidebands are produced, that only small portion of them are sufficient amplitude to be important. For example, the modulation of the 0.5 top spectrum, both view A and B, with the number of the significant sidebands counted as 4. For the next spectrum down, the modulation 1.0, number of the sidebands 6, and so forth. This holds the true for the combination deviation modulation frequency identical modulation indexes. And they show the modulation indexes, significant sidebands. Alright, you should be able to see the setting of the figure 2.9 view A and B with the modulating frequency, determining the space of the sideband frequencies. Using significant sidebands, able to show that the table 2.1 you can determine the bandwidth of the given FM signal with the figure 2.10. A little illustrate for the use of the table of the carrier frequency shown the 500 kilohertz, the modulating frequency of 15 kilohertz, and the deviation frequency of 75 kilohertz. So you have 75 kilohertz over 15 kilohertz would give you a modulation index of 5. Transmitter deviation 75 kilohertz, 500 kilohertz bandwidth. Table 2.1 will show that see that the 16 significant sidebands modulation index of 5. The determinant total bandwidth is for this case U for the bandwidth is equal to the modulating frequency with a number of single significant sidebands. So you have 15 kilohertz times 16, 240 kilohertz. You have the math to illustrate the actual bandwidth of the FM transmitter. 240 kilohertz is greater than the suggested maximum deviation of 75 kilohertz, plus or minus 75 kilohertz, or 150 kilohertz. This is important to know when choosing operating frequency or designing equipment. Method of frequency modulation. Circuit shown with the earlier in Figure 2 of the discussion previous paragraph will illustrate for the purpose of the only with the in reality circuit the circuit would not be practical. However, the basic principle involved the chain of the the reactance for the oscillator circuit in accordance with the modulation voltage constitutes one of the methods of developing frequency modulated wave. Reaction tube modulation. Direct modulation of the oscillator with a frequency modulated with the reactance tube. This is parallel shunt, and is in parallel shunt with the oscillator tank circuit. The term shunt or shunting will be either modulated to be same as parallel or to be placed in parallel with the components. This is illustrated in Figure 211. The oscillator conventional Hartley circuits with the reactance tube. The circuit is parallel with the tank circuit with the oscillator tube. The reactance tube is an ordinary penetrode. This is made to either capacitively or inductively that is grid excited with a voltage that is either leads or lags the oscillator voltage by 90 degrees. Alright, 211 shows the reactance tube of the FM modulator. Modulating radio frequency input and reactance tube oscillator. Alright, this is your reactance tube. Over here, your oscillators on the right. With the reactance of the tube that connected with the tank circuit, there is no modulation voltage applied with the effect of the frequency of the oscillator. The voltage across the oscillator tank circuit with the inductor 1 and capacitor 1 is often in parallel with the series network resistor 1 and capacitor 7. The voltage current the current flow with the resistor 1 and capacitor 7. If the resistor 1 is at least 5 times larger than the capacitive reactive with the capacitor 7, the branch of the circuit will be essentially resistive. The voltage of E1 will cross the capacitor 7 that will lag with the current of 90 degrees. E1 is applied with the control grid reactive of the reactance tube, the chain of the plate current, chains of the plate current, with the essential flow of only through the inductive capacity of the tank circuit because of the voltage value of the resistor 1. How they compared to the impedance of the tank circuit. Since the current is inversely proportional with the impedance of most of the plate current that coupled through the capacitor 3 flow through the tank circuit. At the resonance of the voltage of the current of the tank circuit in favor of the voltage of the E1 lags 90 degrees, and the amperage of it is in favor of the grid voltage E1. The supposed imposed current through the tank circuit lags the original tank current by 90 degrees, but the resultant current caused by the amperage power, amperage P, the tank current lags over the current lag voltage current with the sum of the angle depending on the relative amplitude of the two current because of the resultant current is lagging current. The impedance across the tank circuit cannot be a maximum unless something happens with the tank with the bringing the current with the voltage in the phase. Therefore, the situation continues with the frequency oscillation tank circuit that changes sufficiently so the voltage across the tank of the current flowing with the air into a range again in favor of the action. The same would be the produce of the adding of the reactance of the parallel to the inductor 1 capacitor 1 tank because of the superimposed current lags voltage E dropped by 90 degrees. The introduced reactance is inductive Neets in Module 2 introduction of alternating current and transformers. You've learned that total inductance occur the additional inductive that are added to the parallel, but this introduced reactance effectively reduced the inductance frequency of the oscillator and grew with a new fixed value. Alright, now let's see what happens when the modulating signal is applied with the magnitude introduced reactive to determine the magnitude superimposed current through the tank of the magnitude of the amperage for the power for the given voltage 1, determine the transducer of the V1. Transducer was covered in Neets in Module 6 that introduced the electron emission tube and power flow overlap. The value of the reactance introduced in the tune circuit varies directly with the conductance of the reactance tube. The modulating signal is applied with the grid V1, both voltage E1 and amp change, causing the transducer to vary with the modulating signal with the call of the variable or reactance to be introduced with the tune circuit. The variable reactance either adds or subtracts the fixed value of the reactance for the introduced in the absence of the modulating signal. The action varies the reactance across the oscillator, which in turn varies the instantaneous frequency of the oscillator. The variation of the oscillator frequency are proportional with the instantaneous amplitude of modulating voltage. Reactance tube modulators are usually operated with a lower power level. The required output power is developed by the power amplifier stage valve of the modulators. The output reactance tube The modulated oscillator also contains some of the unwanted amplitude modulation. The unwanted modulation is coupled with a stray capacity resistive component of the resistor capacitor phase splitter. The resistor resistance is much less than significant of the capacitive reactance, but the resistance does also. Some of the plate current of the flow is not proper favor the relationship with the good tube operation. Small amplitude modulation will be produced easily removed by passing the oscillator output through the limit of the limiter amplifier circuit. Semiconductor reactance modulator. Semiconductor reactance modulators use the frequency modulator low power semiconductor transmitter. Figure 212 show the typical frequency modulator oscillator stage operate with the reactance modulator through transistor 1 along the associated circuitry. The oscillator and the transistor transistor 2 with the modulator with the connected transistor 2 is a modulator connected with the circuit with the collector 2, the emitter capacity. The parallel with the portion of the radio frequency oscillator core with induction 1 as the modulator operates with the output capacity of the as the modulators vary, thus the frequency of the oscillator is shifted in accordance with the modulation of the capacitor 1 were varied. Resistance of the semiconductor oscillator show the reactance circuit of the modulation audio frequency input with the transformer, the resistor with 3 and 2 split phase on the transistor, tuning capacitor, tuning reactance tuner, resistor 5 and 6, the capacitor collector emitter, resistor 5, resistor 6, and also I have the oscillator wave going through resistor 1 and resistor 2, transistor 1, capacitor 1, I forget what the arrow means through it, and the induction coil 2, and the transformer and inductor coil from FM output. With the modulation, modulating signal is applied with the base what was transistor 2? The transistor 2 is the modulator. Modulator the emitter base vary with the modulation rate of the cover the collector voltage of the modulator to vary with the semi-modulating rate. When the collector voltage decrease, the output of the capacitor of the collector and emitter, the decrease of the collector voltage, the decrease of the collector and emitter, the increase of the collector voltage, the effect of the strength of the plate of the collector, the capacity of the collector and emitter. Farther apart, with the increase of the width of the barrier, the decrease of the collector of the voltage reduce the width of the positive negative junction and have the same effect for the pushing capacitor plate together to provide more capacity. When the output capacity decreases with the instantaneous frequency of the oscillator tank circuit, the increase as the same as the capacitor 1, decrease the output frequency capacity, increase the instantaneous frequency of the oscillator tank circuit, the decrease of the frequency produced with the lower frequency output because of the shunting effect of the capacitor of the common collector and emitter. Thus, the frequency of the oscillator of the tank circuit increase the decrease of the audio frequency of the AF modulating rate. The output of the oscillator, therefore, frequency modulated with the radio frequency. Since the audio modulation covers the collector voltage, the decrease of the AM component with the induce into the output with the produce the AM, both an FM and AM output. The amplitude variations after they remove the place in the limiter stage after the reactance modulator, only the frequency modulation remains. Frequency multipliers or mixers described in Chapter 1 are used to increase the oscillator frequency, the undesired output, the frequency, high power application linear radio frequency amplifiers are used to increase steady amplitude signal and higher power output of the initial modulation curve at the lower level. The FM represents the saving the power of the wind compared with the conventional AM. This is because of the noise reducing property of the provided the better signal to noise ratio with a possible AM. Multi-vibrator modulator. Another type of the frequency modulators is a stable multi-vibrator illustrated figure 213, illustrating the modulating audio for frequency voltage in the sheet with the base return with the multi-vibrator. The transistor cover the gate length with less than fundamental frequency with the multi-vibrator to vary. The amount of variation will in accordance with the amplitude of the modulating voltage. One of the requirement of the method for fundamental frequency of the multi-vibrator and be in high in relationship to the highest modulating frequency at a factor at least that 100%. At least 100 provides the best results. 213 is stable multi-vibrato filter circuit with a generating FM carrier. Modulating audio frequency voltage transistor 1. Split phase double resonating circuit with the system, the transmitter systematic multi-vibrators, and then you have on your other circuit your capacitor tuning circuits for your frequency frequency modulation and your capacitor resistor and inductor filter. Recall the multivibrator output with each if the fundamental frequency over the harmonics. Unwanted even harmonics are limited with the symmetrical multivibrator circuit as shown in figure 213. The desired fundamental frequency, the desired odd harmonics can be amplified after all the odd harmonics are eliminated with the inductor capacitor resistor. Filter section figure 213, a signal frequency for the modulator carrier with made available for further amplification or transmission. The proper design of the multivibrator will be called the frequency deviation carrier with a faithfully filed with the referred to as linear function of the modulator voltage, true up the frequency deviation, which is a considerable fraction of the fundamental frequency of the vibrator. The principal design with the consideration of the resistor capacitor coupling with the multivibrator transistor base with the collector over the other has time constant with which is greater than the actual gate length by the factor of the 10 or more. Under these conditions, arrive at the base file voltage. Either transistor is essential linear from cutoff of the bias switch. If the transistor is switched on, since the rise of the voltage is linear function with the time of the gate length with the change of the inverse function of the modulating voltage. Action will cover the frequency change as the linear function of the modulating voltage. Alright, the multivibrator frequency modulator, the advantage over the reactive type of the modulator over the greater linear frequency deviation from the given carrier frequency. However, the multivibrator limited the frequency below the 1 MHz of the both system. They are subject to the drift of the carrier frequency and must therefore be stabilized. Stabilization may be accomplished modulating relatively low frequency translating a heterodyne action with the desired output frequency shown in figure 214. A 1 MHz signal is heterodyne with a 49 Hz for the crystal control of the oscillator to provide a stable 450 MHz output with a mixture with a suitable stable heterodyne oscillators used. The frequency stability can be greatly improved with the instance of the frequency shown in figure 214. The stability of the unmodulated 50 MHz carrier would be 50 times better than that of the harmonic multiplication could provide. Figure 214 shows the providing a method of improving the frequency stability of the FM modulating audio frequency stability FM modulator harmonic amplifier 1 MHz plus or minus 75 kHz to the mixer and the crystal control oscillator 49 MHz and then 550 MHz plus the minus 75 kHz Class C amplifier reactor FM modulator. And another FM modulator with the transistorized circuit is used with the voltage variable capacitor vector. A vector is simply a diode or positive negative junction designed to have a certain amount of the capacity between the junction view A. Figure 215 shows that the vector schematic symbol, the diagram of the vector symbol, the oscillator circuit is shown in the view B, but this is not working circuit with a merely simplified illustration. The capacity of the vector is the regular capacity determined in the area of the capacitor plates and the distance between the plates. The depletion region of the vector is a dielectric located between the positive and negative elements in which the surface is played with the capacity is varied in the vector by the varying reverse bias which control the thickness of the depletion region of the vector is designed to the change of the capacity and a linear change of the applied voltage. The special design character of the vector diode. The vector must not be forward biased because it cannot tolerate much current flow, but proper circuit design prevents application from forward bias. 215 show the vector symbol and schematic symbol. Show the diode capacity in a circle that is your vector symbol. Or the diode capacity vector symbol show the inductor on the oscillator circuit. Notify the simple operation of the simple operation from the circuit. Figure 216 audio frequency that is applied with the input or result of the following action on the positive alteration. Reverse bias increase the electrical depletion region with increase with the decreasing capacitance of the decrease of the frequency of the oscillator on the negative alteration of the reverse bias decrease the result of the decrease of the oscillator frequency. Modulated audio frequency input going through the capacitor into the split bias reflect resistor your RFC, and then you have your vector capacitor induction oscillator with a capacitor for FM output. Many different FM modulators are available, but the only basic principles you have to study with the main point with remember the oscillator must have the established with the reference for the carrier frequency. Secondly, some of the methods needed to cover the oscillator change the frequency in accordance with the AF signal anytime that can be accomplished with a frequency modulator. Alright, phase modulation. Frequency modulation requires the oscillator frequency to deviate both above and below the carrier frequency. During the process of the frequency modulation, the peaks of each successive cycle of the modulated waveform occur at the times other than which would if the carrier were unmodulated. This is actually an identical phase shift takes place along with the frequency shift in the FM. Just the opposite action takes place with the phase modulation. The audio frequency signal is applied with the phase modulator in the PM or phase modulation. Thus, the resonant wave of the phase modulator shifter in phase the illustrated figure 217 over the time of the period of each successive cycle varies the modulated wave according to the auto wave variation. Since the frequency of the function in the time period cycle that we can see such of the phase shift in the carrier would cover the frequency change of the frequency change for the FM vital, but in the phase modulation merely nearly identical. The amount with the frequency change has nothing to do with the resonant modulate with the wave shape of the phase modulation. At this point, with the comparison of the FM to the phase modulation may seem a little the phase modulator may seem a little hazy. We will clear up this way as we progress. Audio, unmodulated wave, modulated wave. Alright, let's review some of the voltage phase relations located in Figure 218. Compare with the three voltage A, B, and C with the sense of the voltage A, the given of the cycle reach of the peak of the 4 with the voltage B, the set of the lead with the voltage B. The voltage C, on the other hand, lags with the voltage B with a 30 degree of the phase modulation phase. With the carrier, use the shift of the rate with the modulation signal. Figure 219. Note that the unmodulated signal with the constant phase of the amplitude and frequency that dotted the wave shape with the resonant of the modulated carrier. Note that the phase of the second peak lead with the phase of the unmodulated carrier with the third break third peak with the shift is even greater. However, on the fourth peak with the peak that begin to reline phase with each other, the relationship prevent within each half cycle with each of the air audio frequency modulation signal. On the negative alteration of the audio frequency intelligence, the phase of the carrier would lag and peak would occur at times later than would an unmodulated carrier. Alright, voltage A leads B by 30 degrees, B leads C by 30 degrees, and A leads C by 60 degrees. Figure 219 carrier with or without modulation. The presentation of the two waves together does not mean with the transmitter modulated wave together with the unmodulated carrier. The two waveforms were drawn together only to show how the modulated wave looks compared with the unmodulated wave. Now you have seen the phase of the frequency shift of both the FM and the phase modulator. Let's find out exactly how they differ. The first frequency of the phase shift with the important phase modulator proportional with the audio frequency modulation signal. Visually, this relation prefer the wave shape of the shown figure 220 with the comparison of the phase modulator and frequency modulator and phase modulator wave carefully with the modulating wave shape. You know the phase frequency modulator the carrier the frequency deviation of the modulating wave the change of the polarity with each for the alteration of the modulating wave the carrier advance with the retard of the frequency remain with the new frequency for the duration of the cycle. The phase modulator, you can see between the one alteration and the next, the carrier phase, but must the change with the frequency shift that occurs but does only during the transit time of the frequency, then return with the normal operation. Note that the phase modulator wave, that the frequency shift occurs only when the modulating wave is changing polarity. The frequency during the constant amplitude portion of each of the alteration is the rest frequency. Alright, modulating wave shape, the phase modulation, unmodulated, and the frequency wave modulation. Okay, the relationship of the phase modulation with the modulation air audio frequency with the change of the phase shift with the easy to see. Once you understand the AM and the phase frequency modulator principles, as we again establish with the two clear-cut row of the phase modulation. Alright, amount with the phase shift that is proportional to the amplitude of the modulating signal. If 10 volt signal call with the phase shift with the 20 degree, then the 20 volt signal phase shift will call 40 degree with the rate of phase shift with the proportional of the frequency of the modulation signal. If the carrier were modulated at 1 kilohertz, tone of the carrier would advance the retard in phase by 101,000 times per second. The phase modulation is similar frequency modulation and the number of the sideband but the exhibit within the modulated wave of the space between the sideband and the phase modulation will also produce the infinite number of the sideband frequency spacing between the sidebands will equal to the frequency of the modulation signal have with one over the factor different of the phase modulation. Thus, the distribution of the power of the phase modulation sideband, but not similar to the frequency modulation sidebands as we explained in this next section. Alright, your modulating index. Recall that the frequency modulated with the modulating index is used to calculate the number of the significant sidebands if the waveform. The higher the modulation index, the greater the number of the sideband. The modulation index ratio between the amount of the oscillator deviation of the frequency with the modulation is called the modulation index is equal to transmitter deviation over the modulation frequency. Frequency modulation we see with the frequency modulation signal increases assuming the deviation remains constant, but the number of the significant sidebands paired decreases as shown in figure view A and B with the figure 221. Note that all the total number of the significant sidebands decrease with the high frequency modulation signal with the high band spread out relatively to each other and the total bandwidth increases. Alright, show the frequency modulation, 90 kilohertz bandwidth, the spectrum carrier with the modulated with 5 kilohertz, the 100 kilohertz bandwidth of the spectrum carrier from the modulated within 10 kilohertz. Transmitter, the phase modulation transmitter deviation amount that is saved for all above signals, 50 kilohertz, and the bandwidth, and 100 kilohertz bandwidth. In phase modulation, the oscillator does not deviate the power sideband, the function of the amplitude of the modulating signal. These are therefore two signals, the one at 5 kHz and the other at 10 kHz. Either the modulator with the carrier would have the same sideband power distribution. However, the 10 kHz sideband would either would be farther apart with the shown view C and D in Figure 221 compared with the frequency modulate for the bandwidth of the phase modulation transmitted the signal to greater increase with the frequency of the modulation signal increase. As we pointed out earlier, the phase modulation cannot occur without the incidental change in frequency, nor can the frequency modulation occur without incidental change in the phase. The term frequency modulation is loosely referring to the type of the angle modulation, and phase modulation sometimes incorrectly referred to the indirect frequency modulation. This definition you should disregard to avoid confusion. The phase modulation is just what the word implies. The phase modulation of a carrier by any audio frequency modulation signal. You will develop the better understanding of these points. You can advance in your study of modulation. Your basic modulator. The phase modulation we learn with the varying the phase of the carrier with the intelligence with the rate of the cover through the carrier with the containing variations cover the converted back to the intelligence one circuit that then cover the phase variation shown in Figure 222. Alright, you have your input and output through the capacitor resistor, the phase shifting of the sim wave, and also the capacitor and the shift of the resistor from the phase shift circuit with the constant frequency of the radio frequency carrier to apply the input of the output aircraft. The resistor will be 45 degrees out of phase with the input capacitive reactance equal to the ohms. Now let's the resistance observe the output of the effect of the Figure 223. The reactive reach of the value greater than 10 times the capacitive reactance. The phase difference between input and output is nearly 0 degree. With all practical purposes, the circuit is resistive. The resistance is decreased with 1/10 the value of the capacitive reactive. The phase difference approaches to the 90 degree. The circuit is now almost completely capacitive by replacing the resistor with the vacuum tube as shown in Figure View A. With the Figure 224, with it can be varied with the resistance of the vacuum tube and independent with the varying the voltage applied with the grid over the tube. The frequency applied with the circuit is the crystal controlled master oscillator would be phased and shift at 45 degrees with no audio input. View B, with the application of the audio signal, the phase shift will the impedance of the tube is varied. Show the input A, B, and C. Your variable resistor capacitor, variable resistor position, 45 less than in voltage in, 45 voltage in, more than 45 voltage in, radio frequency input, radio frequency input, the phase modulator, the voltage output. Voltage output, radio frequency relative to the output changes, phase modulator. In practice, all the circuit could not be provided enough phase to shift to produce the desired result of the output. With several of these circuits can be arranged cascade to provide a desired amount of phase shift. Although it's the output of the circuit, it will be varying amplitude. The signal is heavily limited to move with the amplitude variations. Major event of the type of the modulation circuit over the frequency modulation of the circuit over the crystal controlled oscillator to maintain the stable current carrier frequency of the oscillator cannot be crystal controlled because it is actually required to vary in frequency. This means the frequency modulator oscillator will require the complex automatic frequency control AFC system. The automatic frequency control system ensures the oscillator with on the same carrier frequency to achieve a high degree of stability. The automatic frequency control circuit will be covered later in the module. Phase shifting key. The phase shifting key is similar on the on-off continuous wave key with the AM system with the frequency shifting key in the frequency management frequency modulator system. Phase shifting key is most useful to the coded elements for the all code when coded elements are all equal in length. That is all the marks in spaces whenever the message is element synchronizing symbols. Signals occupy the identical elements for the time. It is not fully suitable without you for the starting of the telewriter with the circle with its opposite pulse of 1.42 longer than the other pulse with neither applicable, thus pulse symptoms in the duration position with the pulse with the vary with the modulation frequency simple this over the phase shift keying operates for the principal phase of the reversal carrier with each time of the market to receive the phase is reversed. No phase reversal takes place when the phase space is received. The binary system marks and spaces are called ones and zeros respectively, so that one causes 180 degrees phase shift. The zero has no effect over the incoming signal. Figure 225 shows the application of phase shifting key with the unmodulated carrier view A in the audio frequency range. The transmission over the other conductive path of the wave shown view D must be used in modulating signals. Some of the other systems modulating over the radio frequency carrier. Unmodulated carrier phase shifting key, unmodulated carrier, the modulated signal data element 0010011. Also phase shifting modulating signal data elements. Modulated carrier, CUSP, I don't know what that means. Phase shifting multiplied modulated carrier after filtering. Modulating signal review B consists of the bit stream of the 0 1 0 that does not after the effect of the carrier to frequency, which essentially set the equal the bit rate. For example, the data stream of the 1200 bits per second would have the carrier of the 1200 hertz. When a bit 1 curve of the phase for the carrier to frequency shifted 100 degrees. And if you see, we found that the third path fifth for the second sixth cycle will all have one been reversed in favor of the phasal reversal of the CUSPSs, or sharp phase reversals, will usually remove the filter before transmitting further modulation. Filter action limit the bandwidth of the output signal frequency to the resulting wave shown in view D. The exact waveform of the figure 225 of the VD can be obtained by the basic log obtained by the logical operation of the timing of the data. The illustrated figure in ticket 226 when the timing signal is used rather than the carrier frequency. Data intelligence shown in view B with the combined with the timing signal produced with the combination digital modulation signal shown in view C with the square wave pattern of the digital modulation filter with the limit of the bandwidth of the signal frequency shown in view D with the system has been used in some high-speed data equipment. The others non-practical advantages over the other system modulation practical with the pulse modulated system higher speed data transmission. Alright, figure 226A shows the simulated phase shift king timing. The 226 shows the simulated phase shift king data, and also digital modulation, simulated phase shift king and the digital modulation. Digital modulation after filtering, simulated phase shift king, digitalated modulating after filtering. Or your pulse modulation. Another type of the modulation is pulse modulation. Pulse modulation has many within, including the telegraphic radar, telemetry, multiplexing. For too many of the applications of the pulse modulation, because if the elaborate or any one of these will cover the section, will cover the basic principle of pulse modulation characteristics. Amplitude modulating simple with the radio frequency with carrier with its opponent will become drastically overmodulated that could produce the waveform similar to require the pulse modulation signal of the view A of the figure 227 with a much larger carrier result of the modulation envelope shown in view B. The modulation envelope would be the same as the modulating wave shape, but not syncytial that it looks like one shown in view C. Overmodulation carrier modulation wave show the modulation envelope with the overmodulation with the over the modulation of the carrier modulation envelope. And non-syncytial modulating wave, over modulation of the carrier non-syncytial modulating wave. Observe the modulating square wave in the figure 228. Remember that the contained with the infinite number of the odd harmonic addition with the fundamental frequency. Assume that the carrier with the frequency of 1 MHz, the fundamental frequency modulating square wave with 1 kHz, with a signal with a heterodyne to the new frequency that were produced with the sum of the frequency 1 in 1,000th of a megahertz. The difference of the frequency of the 99,000th of a megahertz. The fundamental frequency heterodyne with this carrier. This also with all the harmonics contained in the square wave of the side frequencies associated with the harmonics will be produced the result of the process. For example, the third harmonic of the square wave of the heterodynes with the carrier to produce the sideband frequency of 1 and 3,000 to 99 thousandths of a megahertz. Another set will have then produced the 5th and 7th, 9th, 11th, 13th, 15th, and 17th, 19th harmonics of the square wave, so that and so on to infinity. Non-modulating wave. Modulating wave. The carrier minus the fundamental carrier plus the fundamental carrier of the third harmonic carrier of the third harmonic carrier and fifth harmonic. Alright, look at figure 228. Observe the relative of the amplitude of the sideband that relate with the amplitude of the harmonics contained in the square wave. Note the first set with the same sideband that were directly related to the amplitude of the square wave. The second side of the sidebands relate with the third harmonic content of the square wave with the 1/3 of the amplitude of the first set with the third set with the relate with the amplitude of the first set with the sideband with the 115 amplitude of the first set with the relationship will apply to each of the additional set with the sideband. View A of the figure 229 show the carrier modulated with the square wave. View B with the modulating square wave. And increase the amplitude with the note the radio frequency peaks. Increase the amplitude during the positive the alteration square wave. The decrease during the negative half of the square wave. And view C with the amplitude with the square wave. The further increase the amplitude the radio frequency wave with almost zero during the negative alteration of the square wave. Figure 229 very rare square wave modulation level of the frequency spectrum carrier than sidebands. Very square wave, figure 229b, square wave modulation level of the frequency spectrum carrier and sidebands. Figure 229c, very square wave modulation frequency of the spectrum carrier and sidebands. Figure 229d, various square wave modulation level of the frequency spectrum carrier and sidebands. Note that the frequency spectrum associated each of these conditions carry amplitude remain with the constant sideband and creep with the amplitude to come up with the amplitude of the modulating square wave. So far the pulse modulation, some of the general apply with the AM in view of the amplitude of the square wave voltage, the equal to the peak of the voltage of the unmodulated carrier wave. 100% of the modulation just conventional with the AM. Note the frequency of the spectrum of the sideband with the distribution of the also the same as the can keep in mind with the total sideband with the 1/2 of the total power over the modulator square and the single square wave of the contrast of the 1/3 of the total wave of the sim wave modulation. Note, now refer to view D with increase the square wave modulation voltage greater than the amplitude of the unmodulated carrier wave. Note that the sideband distribution does not change, but in the sideband, but they take on more transmitted power, so they will carry. So will the carrier. All right, pulse timing. Thus far, we have established a carrier that has covered the peak the decrease of the modulating square wave applied with some pulses. Modulating system of the pulse modulated with the carrier demand for the other produce the no radio frequency until this pulse. The radio frequency occurred during the actual pulse shown in view A of the figure 230. For example, let's start with the radio frequency carrier frequency of 1 megahertz. Each cycle of the radio frequency requires a certain amount of the time to complete. They allow oscillation to occur with a given period of time only during the selected intervals of view B. We are pulsing in the system. Note that the pulsing transmitter does not produce the radio frequency until the one over the positive going modulating pulse is applied. The transmitter then produces the radio frequency until the positive input pulse ends and the input waveform again becomes negative potential. Alright, 230 show the pulse transmission, and 234B show the pulse transmitter. Okay, alright. Referred back to figure 141 overmodulation discussion chapter 1. Well, you will note that the overmodulation wave shape of the view D with the figure 229 of the pulse modulation wave shape of the figure 230 view B are very similar to figure 141. Actually, for the figure 141 view D of the figure 229 result of the overmodulation, even though the output of the pulse transmitter of the 230 looks like an overmodulation, is not, rather it's pulse. However, the frequency spectrums are similar, sideband distributions are similar but not identical. Some of the pulse transmitter figure 230 gated on and off instead of being modulated with the square wave as ways case in view D of figure 229. Remember the pulse modulation sideband produced the accompanying with a carrier during the transmission directly related to harmonic content of the modulating wave shape of the figure 231 view A, view B, view C. Observe the square and rectangular wave shape of the pulsate that modulate the same carrier frequency each of the three views. 231 shows the varying pulse modulated waves, also the varying pulse modulated waves in part B, and the varying pulse modulating waves in time. Let's look at some time relationship of the three modulating sequences in figure 231. The number of the radio frequency signals in the same in each. In the case, the number of cycles that occur with each of the group is different. The ratio between the transmitting and non-transmitting time varies. The transmitting produced the radio frequency wave 4 times in view with the 3 transmission groups in view B, and only 2 in the view C. If the radio frequency is generated only during the positive pulse, in figure 232, they observe the relative of the time of the individual radio frequency with the time of each of the cycle the same with the view and the A, B. The time is the same and was assuming the carrier of the frequencies are the same. They both in view C with the time of each of the cycle will have the views of A and B, but therefore the frequency of the carrier of view C is nearly twice that of the other two. The illustration shows the carrier frequency and pulse systems can vary. Figure 232 and 230A show the carrier frequency, 230B show the carrier frequency, 233C show the carrier frequency. Alright, the carrier frequency only with the frequency must be considered with ourselves with the pulse system. We must also consider the frequency of the associated with the repetition rate of the group and of pulses. Figure 232 shows the specific time period that exists between the each group of the radio frequency pulse. The time is the same with each of the repetition, the pulse called the pulse repetition time. And find out how often the groups of pulse occur with the compute the pulse repetition frequency. Using the formula, pulse repetition frequency is equal to 1 over the pulse repetition time. The time of the pulse repetition the pulse repetition frequency is equal to 1 over the pulse repetition time. Remember that the pulse repetition time is the time it takes for the pulse to reoccur. Shown in figure 234, the duration from the time of the pulse over the time will no pulse occur with a B equals the total pulse relation time. The pulse time and time A plus the time B rest time is equal to 1 pulse repetition time. Alright, time duration of the pulse occurring with the pulse duration or the pulse width. As shown figure 235, as you will see that the pulse width is important to the pulse modulation. Pulse width. Okay, figure show in 235 pulse width. The time we have referring with the time of the no pulse is referred to the rest time. The duration of the rest time determines the certain capability of the pulse modulations for the pulse width at the time of the transmitter produced the radio frequency oscillation with the actual pulse of the transmission time during the non-pulse time. Shown figure 236 the transmitter produces no oscillators cut off. Rest time. Some of the pulse transmitter receive the system of the transmit pulse of the rest of the waiting of the return of the echo of the rest time of the time provided the system of the receiving operation. Your power in the pulse system. Discussion of power in the pulse modulation system. We consider the peak power and the average power. The peak power with the maximum value of the transmitted pulse. Average power of the peak power values average over the pulse repetition time. The peak power is very easily. It's you see in the pulse system in figure 237, the pulse wave shape is the peak power of the 100 watts. They note that the view A, B, and C for the pulse width shape is the same even through the carrier, the frequency of the different. In these cases, the average power would be the same. The basic because the average power is actually equal to the peak of the power of the pulse average over one operating cycle. However, the pulse will be increased in view and will have greater average power of the same phase repetition time. In view E, the describe the pulse will decrease the average power over the same phase repetition time. Peak average power. Each wave shape is over the power peak at 100 watts. Use simple rules to determine the power in the power pulse wave shape. The peak of the power with the maximum power will reach from the transmitter during the pulse. The average power equal to the peak of the power averaging over one cycle. Your duty cycle. The pulse modulation will need to know the percent of the time of the system in which the actual produce the radio frequency. For example, let's say with the pulse system, the transmitter 25% of the time. That means the pulse width is 1/4 of the phase repetition time. For every 60 minutes we would operate a pulse system, would actually transmit a total only 15 minutes. The duty cycle, the ratio, working time of the total time, intermittent operating device. The duty cycle, the representative of the radio, actual transmitting time, the time plus the rest of the time, as doubles the duty cycle, the divide with the phase width and phase repetition time. The field, the duty cycle is expressed with the decimal figure of the information. We can figure the percent of the transmitting time by multiplying the duty cycle by 100%, by 100. All right, the application of the pulse modulation. Pulse modulation has many applications: transmission, intelligent information, telemetry. For example, the width of the successive pulse may tell us the humidity change. The rest of the time may tell us the pressure of the application that you will also see later in this test. Change over the average power they provide with the intelligent information radar pulse. The transmitted travels some of the distance for the target where it can be reflected back to the system. Amount of the time it takes to provide us with the information will be converted into distance. Telemetry radar system principle. The pulse modulation is described in this section. Life the quickly review then has been presented. Pulse width. The duration of the time of the radio frequency is transmitted. The rest time, the time of the transmission resting. No transmission. Carrier frequency. The frequency of the radio frequency wave generated with the oscillator on the transmitter. The pulse repetition time. The time of the one complete pulse cycle with the operation rest time of the pulse width. Pulse repetition frequency of the rate of the pulse of the second. The pulse curve of the power peak. The maximum power contained in the pulse. The average power of the power average over the one complete operating cycle. And the duty cycle, the number of the decimal of the express for the ratio of the pulse modulation shift for the transmit into the total time. The pulse modulation will play with a major part with the electronic carrier in one way or another. You will encounter in some form the function of the particular subsystem when they may involve the variation of the characteristics presented. You will now look at a specific application of pulse modulation radar and communication systems. All right, radar modulation. Radio frequency, energy of the radar transmitted in short pulse of the time duration may vary from 1 to 500 microseconds of the transmitter call before the reflected energy returned from the target they receiver. They can establish between the transmitted pulse and the reflected pulse. After all the reflections have been returned, the transmitter can again be cut on and produce repeated. The receiver, the output will apply with the indicator mentioned for the time interval between the transmission of the energy return of the reflection. Since the energy transfer the constant velocity time of the interval because of the measure of the distance traveled is the range. Since the method that does not depending on the relative of the frequency of the return signal, the motion with the target, difficulties experienced with a continuous wave and frequency modulation methods are not the encounter of the pulse modulation method in many military radar applications. Modulator radar oscillator operates with a pulse voltage of 5 to 200 kilovolts. They require coherence with several amperes during the actual pulse of the play for the several requirements on the modulator. The function of the high vacuum tube modulator is to act the switch from the turn on the pulse on and off of the transmitter in the response of the control signal device. This purpose is one which reads the least signal power of the control, allows the transformer to power of the transmit power source for the oscillator within the least loss. The pulse modulator circuit to discuss the section of typical pulse modulators used in radar equipment. Your spark gap modulator. Spark gap modulator consists of the circuit that is storing the energy, but the circuit is rapidly discharged and storing the circuit with the spark gap. The pulse transformer, the AC power system of the circuit for the storage energy. Essentially a short section of the artificial transmission line, which is known as the pulse forming network. The pulse forming network is discharged with a sparking gap. The two types of spark gaps are used as fixed gap and rotary gap. The fixed gap is discussed with the section when you use the trigger pulse with the ionize the air between the contact with the spark gap. The initiate the discharge of the pulse forming network. All right, the rotary gap is similar to mechanical driven to a mechanical driven strip. The typical and fixed spark gap modulator circuit is shown figure 238 between the trigger pulse with the spark gap is an open circuit with a current flow through the pulse transformer 1 of the pulse forming network, capacitor 1, 2, 3, 4, and inductor 2, the diode V1 and the inductor 1, and the plate supply voltage. These components form a charging circuit with a pulse forming network. Figure 238 shows the fixed spark modulator. You have the place voltage bias the inductor to the diode, the trigger pulse, and then you have the capacitor going to the spark plug, the capacitor 1, 2, 3, 4, positive. And then you have a phase modulator, which transistor 1 to the magnetron. That is basically a distributor for a car. The spark gap is actually triggered over the ionized combined action with the charging voltage across the pulsing formed, and that with the trigger hole for the ionization to discover the Neets module 6 introduce electronic emission the tubular power supply. There, between the trigger pole for the injection point with the ground is ionized, with the trigger volt for the distance from the ionization over the complete gap of the charging voltage of the ionization that allow for the condition of the charging pulse forming the network through the pulse transformer T1. Output pole for the supply with the oscillating device such as the magnetron. The thiatron modulator. The hydron and thiatron modulator's electronic switch with the result of the pop of the trigger only 150 volts. The trigger potential must rise at the rate of 100 volts per microsecond to caliber the modulator to conduct. This contrast with the spark device the hydrogen thiatron operates over the wide range of the anode voltage of the pulse repetition rate with the grid complete with the control over the initiated cathode emissions over the wide range of the voltage. The anode is completely shielded with a cathode by the grid. The effect of the grid action results in very smooth firing over the wide range of the anode voltage repetition frequency. Upon most of the other thiatron, the most of the positive grid control characteristics to ensure the stable operation. In addition, the deionization time is reduced using a hydrogen-filled tube. Alright, the thiatron gas tube monitor show the diode, thiatron trigger pulse, and the voltage bias, the capacitor resistor 1, resistor 2, diode 2, your capacitor spark plugs in transformer 1 magnet to magnetron. The hydrogen thiatron modulator provides the improved timing because of the synchronized trigger pole that they apply with the control grid. Thiatron instantaneous firing is obtained. In addition, only the gas tube is required to discharge the pulsing form of the net with low amplitude trigger pole sufficient to initiate the discharge damping diode to prevent the back breaking down the thiatron reverse voltage transistant. The thiatron requires the sharply edge of the trigger pulse that depends on the sun. The drop of the anode voltage control of the pulse forming a net with the terminate the pulse and then cut off the tube is shown in figure 239 with the typical thiatron modulator is very similar to the spark modulator or spark gap modulator and consistent power over the voltage of the circuit is shown with the inductor 2, capacitor 2, 3, and 4, and 5. The circuit is for the discharging voltage circuit. V2, the pulse transformer, in addition to the circuit of the damping diode of the V1, prevent the reverse polarity signal with the applied with the plate with the V2, which could cause the V2 breakdown. With no trigger pull over the P and F, PF and N chart of the transformer 1 of the PF and N chart of the coil with the L1, the potential of the voltage bias with the trigger pull of the applied with the grid with the voltage 2, V2 the tube band over the cause of the pulse forming net with the discharge of the V2 of the primary transformer 1, the voltage across the PFN below. Ionization points involved V2 the tube shows because of the inductive property of the PFN part of the discharge voltage with the tendency to swing the negative overshoot prevented with the damaging of the thiatron affecting the output of the circuit vector diode 1, resistor 2, capacitor 1, the damping circuit provides the path of overshooting of the transistor of the diode 1 dissipated with the resistor 1 and resistor 2, capacitor 1 acting as a high frequency bias bias to the ground, preserving the sharp leading of the trailing amp of the pole for the hydrogen thiatron modulator, most common radar modulator. Alright, your pulse modulation useful communication system, intelligent carry capability. The power requirements communication system different from those of the radio. Therefore, the method of the achieve the pulse modulation, the more suitable the communication system will now be studied. Alright, communications and pulse modulator. To transmit the intelligence of the use of the pulse modulation, you must provide the method to vary some of the character of the pulse drain and core for the modulation cycle. The figure 240 illustrates the symbol of the pulse drain, but the character of these pulse may vary in the amplitude of the pulse width, the pulse repetition time, pulse position, or compared to the reference addition, with the three characters of the pulse must be transmitted in accordance with the code of the representative of the different level of the modulating signal. The extreme of the maximum fidelity, accuracy, reproducing modulating wave. The modulating signal that has been represented enough pulse to restore the original wave shape. Logically, the higher the sample rate, the more often sample the pulse modulated, the more accurately the original modulating wave reproduced. Figure 241 illustrates the effectiveness of the three-pulse sampling rate. The V2A shows the sampling rate of more than 2 times of the modulating frequency. As you can see, the reproduced modulating signal varies accurately with however the highly sampled rate of the curves requires wide bandwidth and increase the average power required for the transmitter. If less than 2 samples per cycle, you are not able to reproduce the original modulating signal. Shown the UB and the VUC, showing the sample rate with the 2 times high modulating frequency. This minimum sampling rate will give you sufficient accurate reproduction of the modulating wave. The standard sampling rate with 2.5 times the highest frequency that is to be transferred and ensure the ability of the accurately reproduce the modulating waveform. The military voice system with the bandwidth for the voice signal is limited to 300 to 3,000 Hz, requiring sample frequency of 8 kHz. Although the pulse character of the chain may vary for each type of the pulse modulation, same frequency will remain constant. We'll now briefly discuss common types of the pulse modulation. Alright, phase pulse width, pulse repetition time, amplitude, pulse train. The more than 2 pulse samples within every wave. The pulse sample, the more than 2 pulse samples of every wave. The less than 2 pulse samples for every wave. Pulse system sample less than 2 pulse samples for every wave. The 2 pulse samples for every wave. The pulse sample rate, the 2 pulse samples for every wave. Pulse amplitude modulation. Some characters for the sample of the pulse must be varied with the modulation signal. The intelligent signal represented by the pulse wave. Figure 240 show the 3 typical waveforms of which the pulse amplitude varied amplitude with modulation signal. View A represents the sim wave, the intelligently modulated, the transmitted carrier wave. The view B show the time pulsing with which determine the sample interval. With the view C show the pulse amplitude modulation or PAM. In the which amplitude with each of the pulse in control of the instantaneous amplitude with the modulation signal at the time of each pulse. Figure 242 show the pulse amplitude modulation, the timing, the pulse amplitude modulation PAM, the timing, pulse amplitude modulation itself. The pulse amplitude modulation is a simple form of the pulse modulation. It generally is generated much of the same manner with the analog amplitude modulation, and the type of the pulse they are applied with the pulse amplifier, which for the gain is control of the modulation waveform. Since the variation of the amplitude actually represented the signal of this type of the modulation basically form of the analog amplitude modulation, but the only difference with the signal is known that the form pulse of the mean of the pulse amplitude modulation has the same built with the weakness of the analog amplitude magnification signal. High suspectability noise interference. The reason for the suspectability noise of the interference with the transmission path will either add or subtract any of the voltage already in the circuit. The signal voltage of the amplitude of the signal will be changed. Since the amplitude of the voltage represented the signal unwanted change, but the signal conserves the signal distortion. For this reason, the pulse amplitude modulation is often used. The pulse amplitude modulation, the pulse of the train is used. The frequency modulator, the carrier from the transmission. Techniques for the pulse modulation other than the pulse amplitude modulation have been developed to overcome the problems noise interference. The following sections will discuss other types of pulse modulation. Alright, pulse time modulation. Pulse modulated system is an analog system. The intelligence may be improved with the carrier by varying any other character of the previous paragraph. The method of modulation of the pulse train varying of the amplitude will discover the time and character of the pulse may be also modulated with the intelligent information 2-time character that may be affected with the time duration of the pulse, referred to the pulse duration modulation, and the pulse width modulation. The time occurrence with the pulse referred to as the pulse position modulation, or the special type of the pulse timing modulation referred to as the pulse frequency modulation. Figure 243 shows the type of the pulse timing modulation. View C and D and E. The view A and B show the pulse modulating signal time respectively. 243A show the pulse time modulation. 243 show the pulse timing modulation timing, and then 243C show the pulse timing modulation pulse duration modulation unmodulated width. Unmodulated positions of the pulse position modulation. Pulse timing modulation pulse. There's a lot of them. Pulse frequency modulation of the pulse timing modulation, pulse frequency modulation. Alright, your pulse duration modulation. The pulse duration modulation, pulse wave, pulse width, pulse duration modulation, or pulse width are designed a single type of the modulation with each of the pulse of the train is made a proportional with the instantaneous value of the modulation signal, the instant of the pulse. For each leading edge of the trailing edge, the pulse edge of the pulse must be modulated to produce the variation pulse width. The pulse duration modulation can be obtained with a number of the weights, one which is illustrated in view A through D in figure 244, and circuit to produce the pulse duration modulation shown in figure 245. adding the modulating signal to figure 244 and view A as repetitive sawtooth view of the B will result in the waveform shown in view C. The waveform is then applied with the circuit at which the change state of the input signal exceeds the specific threshold level of the action produces the pulse with which will determine the length of the time the input waveform exceeds threshold level and the result of the waveform shown in view D. Alright, figure 244A show the pulse duration modulating signal. 234B show the pulse duration modulation signal, repetitive sawtooth pulses, and also the pulse duration modulation signal and the sawtooth added. 244D show the width of the modulating pulse of the circuit and shown in figure 245. The pulse duration with the which modulated pulse of the circuit of figure 245 show the 245 show the circuit of the producing pulse duration modulation sawtooth pulsation generation voltage input voltage secondary modulating signal collector voltage the two transistors sharing a split network of resistors in the transformer 1 pulse duration mounting output variable position fixed position. Alright, in this circuit, the figure 225, the shear of the sawtooth occurring with the sample rate applied with one shot with the multivibrator, signal the voltage, the voltage supersedes the bias voltage and the AND voltage input. Each pulse triggers cycle of the multivibrator after the determine the ether time intervals vary linear with each voltage over the secondary. The pulse of the plate with the voltage of the multivibrator with the leading of the edge of the transformer 1 leading edge vary the position of the signal voltage of the trailing edge of the transformer 2 takes the determination of the sawtooth leading of the output pole of the duration with the width of modulated sawtooth as instantaneous build up of the sloping trailing edge of the leading edge of the transformer 1 is fixed with the trailing edge of the transformer 2. Sawtooth generated with the slope on the both of the leading edge of the trailing edge of the both transistor 1 and transistor 2. The vary of the position result of the system result in still the pulse duration modulation as often used because of the constant amplitude, therefore the less susceptible noise compared with the pulse position modulation. Pulse duration modulation have the disadvantage varying pulse width and therefore varying power content. This means that the transistor must be powerful enough to handle the maximum width pulse, although the average pulse power transmitted is much less than the peak of the power. On the other hand, the power pulse duration modulation will still work if the synchronizing between the transmitter and receiver fail. The pulse position modulation will not, as we will see in the next section. Alright, your pulse position modulation. The amplitude and width of the pulse is kept the constant with the shift of the pulse position. Each of the pulse relation pulse of the recurrent reference pulse vary with each of the instantaneous sample vary with the modulation wave. The pulse position modulation has the advantage of requiring the constant transmitter power since the pulse with the constant amplitude variation is widely used but has a disadvantage depending on the transmitter receiver synchronization. Alright, your pulse position modulation can be generated in several ways, but we will discuss that on one of the simplest figure 246 wave that's associated with the developing pulse position modulation from pulse duration modulation. Pulse duration modulation pulse training is applied with the differentiation circuit. The differentiation was discovered present in the Neets module 9 introduction wave generation wave shaping circuits. This provides the positive negative polarity pulse that corresponding to leading the trailing of the positive duration modulation circuits or positive duration modulation pulses. Considering a positive pulse duration modulation generation, you can see that the pulse of the leading and trailing edge. In this case, the pulse position of the leading edge, the fixed wherever the trailing edge of the dot is shown view A of the figure 246 for the resultant pulse after the differentiation is shown view B. The negative pulse of the position of the modulated in accordance with the modulating waveform, that both the negative and positive pulses are applied with the rectification circuit. This amplitude, this application eliminates the positive non-modulated pulse of the developing positive pulse position modulation pulse train as shown in figure view C. View A duration modulated pulse train unmodulated position with the trailing edges and also pulse train after the differentiated edges pulse pulse position pulse train obtained with the rectifying and pulse 2 figure 46 throws the pulse position modulation Alright, your pulse frequency modulation. Pulse frequency modulation method of the pulse modulation, which the modulating wave is the frequency modulated with the pulse generated. For example, the pulse rate may be 80,000 pulses per second when the signal voltage is 0. The pulse rate may step up to 9,000 pulses per second. For example, the maximum pulse signal voltage is down to 7,000 pulses per Second, for the maximum negative signal voltage of the tip, you get two view A, B, and C for the typical waveforms of the pulse frequency modulation. The method of the modulation is not used extensively because of the complicated pulse frequency modulation generators method that requires the stable oscillator that is frequency modulated to drive the pulse generator, since the other form of the pulse timing our modulator are easier to achieve. They are commonly used. Figure 240 for the bulk frequency modulator modulation. Pulse 240 for the B show for the pulse frequency modulation timing. Pulse frequency modulation. And the third one, pulse code modulation. Alright, pulse code modulation, or PCM, refers to the system of the standard value of the quantized wave that explained with the following graph that indicate with the series of the code pulse. When the pulses are decoded, they indicate the standard value that originated the quantized wave. These codes may be binary, in which the symbol of each of the quantized element consists of the pulse space of the tension area, which code each of the element consists of one of three distinct kinds of values, such as positive pulse, negative pulse space, as are in area, which are code for each of the element, but consists of made of the number n, and the distinct value of the discussion may be discussed in binary positive code modulation system. Alright, also all of the pulse code modulation systems discussed previously provide method for the converting analog wave shape with the digital wave shapes. The pulse occurring with a discrete interval, some of the characters of which the varied with the continuous function of analog wave, the entire range of the amplitude, frequency or phase value of the analog wave can be arbitrarily divided in series with the standard value of each of the pulse or pulse train. Figure 248 view B, the take of the standard value nearest to the actual value when modulated. The modulating wave can be faithfully reproduced as shown view C and D. Amplitude range has been divided into 5 standard values of view C. Each pulse was whatever the standard value is nearest is the actual instantaneous value. In view D, the same amplitude range has been divided into 10 standard levels of view. Current view D is much closer than the approximation modulating wave view A. This is in 5-level quantized curve in view C, from which you should see the greater number of the standard level that you choose, the more closely quantized wave the approximates the original, or this also made evident by the fact that the infinite number of the standard level exactly duplicate for the condition of non-quantization original analog waveform. Alright, 248A show the quantized level of modulation. 248B show the quantized level of timing. The quantized level of 5 level, the quantized level of quantized level of 10 levels. Although quantization curve of the figure 248 based on 5 to 10 level of quantization equal to the practice level, usually establish some exponential value of 2, such as 4 to the 2 times 2, or 8 times 2 to the third, or 16 times 2 to the fourth, or 3 to 2 times 10 to the fifth, or n times 2 to the nth, reaching with the selecting level, the exponential level value of the 2 will become evident within the discussion of the positive code, pulse code modulation, quantized frequency modulation, similar everywhere of the amplitude analog modulation. This range of the frequency of the duration divided by the finite number of the standard value of the deviation each sample pulse result, and the deviation equal to the standard value of the nearest the actual deviation sample is this instant. Similar for the phase modulation quantization established for the set with the standard value of the quantization is usually mostly amplitude of the frequency modulating pulse system. Figure 249 shows the relationship between the decimal number of the binary number of the pulse code of the waveform of the representative of the number of the table is for a 16 level code. The 16 standard values of the quantized wave that could be represented by each pulse group. Only the presence and absence of the poles that are important. The next step of the wave is 32 level code. Each decimal number is represented by a series of 5 binary digits rather than 4 digits. The figure 249, 6 digits groups were divided by 64 level code. 7 digits codes are 128 level code, and so forth. And figure 250 show the application of the pulse code grouped in the standard value of the quantized wave. Alright, decimal numbers 0 through 15 show the binary equivalent and the pulse code waveform. Ranges of the standard values, code values. In figure 250, the solid curve of the reps of the unquantized value of the modulating sinusoidal discharge curve, the reconstructed the quantized value of the take of the sampling interval shown with the variable, the closing arrangement, the original curve, figure 251, identical to 250, except the sampling interval with the 4 times greater the reconstructed curve that is not faithful to the original. It is previously stated that the sample rating of the pulse system must be at least twice the highest modulating frequency to get a usable reconstructed modulating curve. The sample rate of the figure 250 in the 4-element binary code of 128 bits present in the absence of the pulse must be transmitted each cycle of the modulating frequency at a sample rating of the 251, or only 32 bits are required. Minimum sample rate with only 8 bits are required. Our range of standard values 0 to 16 code values As a matter of the conveyancy, especially the simple of the demodulation pulse code modulation, the pulse training actually transmitted reverse from those shown in figure 240, 250, and 251. That is for the pulse with the lowest binary volt value, least significant digit that transmitted first. For the succeeding pulse that has increased the binary value of the up to the code limit, most significant digit pulse coding can be performed with the number of the waves of which conventional circuit may be spinning to the specific code rate. Coding tubes, the one form of the coding circuit is shown in figure 252 in the case for the pulse sample that are applied with the holding circuit capacitor, which stores pulse amplitude information. The modulator converts the pulse amplitude modulation to pulse duration modulation. Pulse duration modulation must then be the gate output with the precision pulse generated with the control of the number of the pulse applied to binary counter. The binary counter. The derivative of the gate pulse is not necessarily the integral number of the repetition of the pulse with the precisely time of the clock pulse generated. Therefore, the clock pulse for the gate in the binary counter with the pause by positive duration modulation pulse may be the number of the pulse plus the leading edge of the additional pulse. This partial pulse may have significant duration when the trigger is that the counter, or it may not. The counter thus responds only to the integral number. The effect of the quantizing the signal while at the same time as encoding it with each bistable state of the counter store of 0 and or 1. Each binary digit represents a 1 1 or 1 1 1 0. For decimals, 14 shown in figure 252. The electronic communicator sample is 2 0 to 2 1. 2 to the 0th, 2 to the first, 2 to the second, and 2 to the third digit. Position sequence to transmit with the mark and space, the pulse, and no pulse for the corners for the state, each for the counter state of the holding circuit is always discharge result of 0 before the initiation of the sequence of the next pulse sample. Pulse samples, a holding circuit with a pulse duration modulator, gating circuit with a clock pulsator, generator, binary counter, electronic commutator, positive pulse code modulator output. Figure 252 shows the block diagram of the quantizer and the pulse code modulator coder. All right, the pulse code modulator demodulator will produce the correct standing amplitude represented with the pulse code group. However, the reproduce for the correct standing only if the applicable to recognize the current present of the absence of pulse for each position. For this reason, the noise introduced no error with all of the signal to the noise ration and such with the largest peak of the noise is not mistaken for the pulse of the noise. The random circuit of the tube noise, the probability of the premium of the noise peak with the comparable to the amplitude of the pulse can be determined. Probability can be determined mathematically. Any ration of the signal to the average of the noise power. Whenever this is done with the 10 to the 5th pulse per second, the approximate error with the rate of the three values signal powers to average noise power loss is 17 decibels, 10 errors per second at 20 decibels, 1 error to every 20 minutes, 22 decibels every 2,000 hours. Alright, above the threshold of the signal noise ratio, approximately 20 decibels, virtually no errors occur. In all the other system modulation, even with the signal noise ratio, the higher than 60 decibel noise will have some of the fact. Moreover, the positive code modulation, pulse code modulation signal will be retransmitted with a multiple relay link system that many type of the desire without the reintroduction of the additional noise effect. With the noise not cumulative at a relay station with the other modulation system. The system does of course have the distortion and truth to do with the quantizing signal for the both of the same value like for the sampling interval intended to make with the reconstructed wave part of the depart with the original with the distortion called the quantizing nor with the initial introducing the quantizing code modulator remains the fixed throughout the transmission to retransmission process. The magnitude can reduce making the same quantization level to close together. The relation to the quantizing noise of the number of the digits binary code is given in the following understanding of the relationship where n is the number of the digits of the binary code. The peak signal power over the average quantizing noise power is equal to 10.8 or 6 to the nth decibels. Thus we have 4-digit code, the figure 250 and 251. The quantizing signal will be 35 decibels weaker than the peak signal, with the channel will be accommodated the advantage of the positive code modulation. Pulse code modulation twofold. The first noise interference must be almost completely eliminated when the pulse signals exceed the noise level of value of 20 decibels or more. Second, the signal may be received and retransmitted as many times as many desired with introducing distortion into the signal. Chapter 2 Summary.